space, time. These are the fundamental building blocks of our universe, or so we thought. Einstein revolutionized our understanding of these concepts with his theory of general relativity. He taught us that space and time are not separate entities. They are interwoven into a four-dimensional fabric called spacetime. Imagine a trampoline. This represents the fabric of spacetime. Now, place a bowling ball on the trampoline. The ball creates a dip, a curvature in the fabric. This is akin to how massive objects like stars and planets warp the fabric of spacetime. But what if spacetime itself is not uniform? What if it has inherent curves and anisotropies, even in the absence of massive objects? This is the radical idea we're going to explore. It challenges our conventional understanding of the cosmos. Initially, the universe expanded isotropically, with uniformity in all directions. However, as the universe evolved, localized dynamic curvature of four-dimensional curved spacetime with de Sitter symmetry and Planck-scale twists may have led to anisotropic expansion. These mysteries include Hardy's paradox, the Hubble tension, and the CMB Cold Spot. These are puzzles that have baffled scientists for years. They seem to defy our current understanding of physics. By embracing the concept of a four-dimensional curved spacetime with de Sitter symmetry, we can begin to unravel these cosmic enigmas. Planck-scale twists and dynamic spacetime curvature could redefine dark energy as an emergent property of spacetime's evolving geometry. Early universe observations show a lower expansion rate, while local observations indicate a higher expansion rate. Localized variations in dark energy and curvature might explain these discrepancies. Planck-scale dynamics could have affected early energy distribution, leading to dynamic curvature and localized cooling. A unified model of probability, expansion and CMB anomalies could offer an observational reinterpretation of cosmological anomalies. This new perspective might just be the key to understanding our universe. Let's delve into the strange world of quantum mechanics. Here, particles behave in ways that defy common sense. They exist in multiple states at once, a concept known as superposition. This fuzziness creates paradoxical situations like Hardy's paradox. Imagine two particles on a collision course. Quantum mechanics tells us they can interact in a way that seems impossible. Even if they both take separate paths that avoid a direct clash, their quantum states can become entangled. This entanglement means their fates are intertwined. Hardy's paradox arises when we consider the particles after their near miss. There's a chance that one particle will be measured in a state that suggests a collision occurred even though it didn't. This paradox highlights the weirdness of the quantum world. How does four-dimensional curved spacetime fit into this? Imagine our particles moving through this dynamic curved spacetime. Not just space, their paths now through time as well as space become intertwined. This interconnectedness allows for seemingly impossible interactions. The concept of non-zero minimal instance is key here. Think of time not as a smooth flow, but as a series of incredibly tiny, discrete moments. These moments, though minuscule, are not infinitely small. They represent the smallest possible unit of time. In this framework, the particles' paths through space-time can overlap within these tiny instants. This overlap resolves the paradox, allowing for the observed entanglement without a direct collision in the traditional sense. Thus, superposition can be redefined in light of our resolution to Hardy's paradox. It's not just about particles existing in multiple states, but also about their paths overlapping in the fabric of four-dimensional spacetime. In this context, dark energy can be redefined as the influence of these overlapping paths in four-dimensional spacetime. It's the unseen force that drives the dynamic interactions and entanglements of particles, shaping the universe at the quantum level. This redefinition helps us understand dark energy not as a mysterious force, but as an integral part of the quantum conundrum within the curved fabric of spacetime. The resolution of Hardy's paradox using non-zero minimal instants and curved spacetime has profound implications. It suggests that time itself might be more complex than we perceive. What if instead of a straight line, time is a loop? Imagine a Mobius strip. It has only one side and one edge. If you follow the edge, you'll eventually end up back where you started. This closed loop is similar to how time might behave in a four-dimensional curved spacetime. This concept of closed-time geometry might seem strange, but it elegantly explains how particles can interact without directly colliding in the traditional sense. They are connected through the loop of time, their paths intertwined in this closed-time geometry with Planck-scale twists. It means that the past, present and future might all be connected in ways we are only beginning to understand. It challenges our linear perception of time and opens up exciting new possibilities for exploring the universe. Non-zero minimal instants and Planck-scale twists redefine our understanding of dark energy. Within this curved spacetime framework, dark energy is not just a force driving the universe's expansion. Instead, it is intricately linked to the very fabric of spacetime, influenced by the Planck-scale twists and closed-time geometry. These concepts integrate seamlessly, offering a new perspective on the universe's structure and the role of dark energy within it. Section 4. The expanding universe. Hubble's tension arises. Let's shift our focus to the grandest stage of all, the universe itself. We know that the universe is expanding. Distant galaxies are moving away from us, and the farther away they are, the faster they seem to recede. This is Hubble's law, a cornerstone of modern cosmology. However, there's a problem. When astronomers try to measure the rate of this expansion, the Hubble constant, they get different answers depending on how they measure it. This discrepancy is known as the Hubble tension. It's like trying to measure a room with two different rulers that give you different lengths. This tension throws a wrench into our understanding of the cosmos. It suggests that our current models of the universe might be incomplete. In this context, dark energy, which drives the universe's accelerated expansion, might need to be redefined. Could four-dimensional curved spacetime within de-Sitter symmetry with Planck-scale twists hold the key to resolving this tension? This is going to blow your mind. Section 5. Cosmic twists and turns. A new perspective on expansion. Remember the trampoline analogy for space-time? Now imagine that the trampoline isn't perfectly flat. Instead, it has subtle twists and turns representing the inherent curvature of space-time. These twists and turns would make the expansion of the universe more complex. The rate of expansion wouldn't be uniform everywhere. It would depend on the local curvature of space-time. This could explain why we observe different values for the Hubble constant, addressing the Hubble tension. Imagine measuring the expansion rate in a region of space-time with a slight twist. The measured rate would be different from a region with a different curvature. This variation in expansion rates could be the missing piece of the puzzle. Adding to this, consider the implications of Planck-scale dynamics. At the incredibly small Planck scale, the fabric of space-time itself might be subject to quantum fluctuations and uncertainties. Quantum fluctuations are temporary changes in energy that occur spontaneously at the smallest scales. These fluctuations could further contribute to the context-dependent expansion rates. Redefining dark energy within this framework also provides a potential resolution to the CMB Cold Spot. The CMB Cold Spot could be a manifestation of four-dimensional curved spacetime with de Sitter symmetry and Planck-scale twists. This framework suggests that the Hubble tension isn't a flaw in our observations. Instead, it's a clue. It also offers a new perspective on resolving Hardy's paradox by considering the quantum fluctuations at the Planck scale. This new perspective opens up exciting avenues for research and deepens our understanding of the universe's evolution. Initially, the universe expanded isotropically, with uniformity in all directions. Shortly after this initial phase, Planck-scale dynamics led to anisotropies, marking a significant shift in the universe's evolution. This transition resulted in the complex structures we observe today, driven by the localized, dynamic curvature of four-dimensional curved spacetime with de Sitter symmetry and Planck-scale twists. Traditional views consider dark energy as a constant force driving the acceleration of the universe's expansion. In contrast, this proposal views dark energy as a dynamic property emerging from the curvature and twists in four-dimensional anisotropic spacetime with closed-time geometry influenced by Planck-scale dynamics and quantum fluctuations. So could this be the key to understanding the universe's true nature?